So now in this video we have the op amp wired as an inverting comparator. So it's basically the same circuit that we did in the last video, the non-inverting comparator, except for the inputs are swapped, and you can't swap their location on the physical component. So I shuffled the other components around, but on the schematic diagram you can shuffle them. But remember, when you're using the actual component, you gotta know the pin layout. So, look at the data sheet, or hopefully you buy it in a kit that shows it. The symbols are alternated on here, so always be aware of that. Plus, this doesn't always have to point to the right. Maybe it's like pointing down or pointing up, so, the inputs could be anywhere. But especially when it's pointing this way, because you may not realize it, the plus and the minus may not line up with what's on the actual integrated circuit. So it is an inverting comparator. You can see the red LED, we got the negative supply there, so we know that the output is high, that current is flowing in that direction. And we are using at least 12 volts. So we need significant resistance there, about 1.5K instead of 220, which I use for 5 volts. That's one reason why I'm showing these 12 volt circuits, because 12 volts is kind of common now. So in any case, we got that low input with a high output. So it's lower than the voltage we set there. We need a reference voltage when we use an op amp as a comparator, or a comparator integrated circuit as well. So in any case, I went closer to the positive supply right there. It's going to that positive row. I know it's kind of blocked, and so that is a positive row there. The gray jumper is going to the negative row. We are closer to the positive. Again, this sets it halfway, so we are more than halfway towards positive. Halfway mark right there. So these are 10K resistors. Right now, we got like a little less than 5K, because this is a 10K trim pot, to the positive supply, and more than 5K to the negative, making it a higher voltage than half the supply voltage, higher than 6 volts at this time. So the output's low. And we know that because the resistor there goes to the positive supply before it comes to the long lead. Make sure you put it in the right way of the LED, and the short lead down here, cathode. So we know, since that's positive supply, that we are headed to ground right there. The output is low, the best that it can be. It's not a direct connection. It goes through transistors. Same when the output is high. But the main thing is lower voltage input than our signal voltage gives a high output, a higher voltage. Whereas the high input right there, in comparison to the reference voltage there, gives us a low output. It is inverted, and there's many ways, or many reasons why you may want to do that. So we're not going to go on that in this video. Just knowing the circuit is enough. So again, this 12 to 14.6 volts, if you are working with 12 volt circuits, good chance you are using lithium iron phosphate batteries. There's also lithium ion batteries in a lot of circuits as well, but lithium iron phosphate is probably the main one you might use, especially if you're like powering your house and stuff for backup storage. Also, there's like 24 volt, 36, and whatever. But when you apply a charger to those batteries to get the most charge into them, you get almost 15 volts. 14.6 is the maximum voltage you want to apply, but that could pump the maximum charge into them, and then when you stop charging, when they don't accept any more charge, you should stop charging it, because it's not good to just keep applying this higher voltage forever. It'll drift down to 13.6, but we have the potential of 14.6 volts going across a circuit if it's a 12 volt circuit. So I made sure to account for that. So instead of a 1000 ohm resistor, which you could use for 12 volts, I got 1.5K. So it'll limit current a little bit more through the red LED, but it'll keep the resistor from getting too hot. 1000 ohm resistor, I stopped using it at 12 volts, even when I have a red LED dropping a couple of volts from it. We also have the supply of the op amp. Doesn't completely go to the positive supply. So we are safer than, we need to be, but it's still good to be extra safe. And then ground connects better than the positive supply, but with the load it's still won't go all the way to ground. But blue LEDs are pretty bright, so I got a 3000 ohm resistor for that one. So we'll look at that. And again, we got 10K resistors for our voltage divider. But you can see the blue LEDs are already brighter, even though it has, you know, twice the resistance right there. It's probably pretty close to twice the current that's going through the red LED versus the blue LED. But the blue LED probably still is brighter. So about 7 milliamps of current. This isn't as accurate as a multimeter for the red, and about 4 it looks like for the blue LED. Plus there's, you know, some other currents flowing through. This is a 10K trim pot, as I said before. So at 10 volts, we got about 1 milliamp of current just going through the trim pot. So that's going to be part of this right there. So be aware of that as well. But any case, we have a circuit that will work pretty well. And of course, the 10K trim pot, you wouldn't really make a circuit like this. Why would you want something? You could just do an on-off switch. You don't need, you know, to turn a trim pot. But there's a lot of sensors. You know, like you could take a light-dependent resistor. You would also use a fixed resistor. You could take a light-dependent resistor, either put it on the high side or the low side, and that voltage will drift above and below the halfway point, depending on how much light is falling on the light-dependent resistor. And there's a number of other sensors that are resistance-based where you get a voltage divider. So this would usually be worked with one of those sensors, but this is for the visual right here. You can actually see me sliding this, and when I have an oscilloscope in some of my videos, those aren't very popular though, you can actually see the voltage sliding up in this case, or down as I turn the trim pot. So once you can visualize that, that's what I visualize. The voltage just went down and now it's sliding right up. That's what I always visualize when I see a trim pot like this wired as a voltage divider. Of course, you could use it as a variable resistor. So let's go with the notes again. You can go up to 32 volts with this op amp. The main thing is limiting current so you don't burn anything out. As voltage goes up, it gets more and more important to limit current or get higher wattage components as well. The input doesn't really sink or source a lot of current. It should have short circuit protection though. Hopefully if you wire it up to something and it asks for more current than the op amp can handle, hopefully the op amp will just limit it. It will protect itself, but I don't know if that's always the case, but thought I'd mention that. So we can go up to 32 volts. If it's a split supply, that's when ground, there'd be like a negative voltage, negative 12 volts, and ground would be there. We'd have 12 there. So ultimately, that's a total of 24 volts. So that's why single supply is twice the voltage of a dual supply. Now, the output is high. That means it's sourcing the current. So you consider that to be the source, working positive towards negative, and then the output, when it's low, that's considered sinking the current. Again, it goes through transistors. You don't make a direct connection, but you make as good of a connection as that particular op amp can make. Some of them are rail to rail, and they can go the full range of the voltage if there's no load. Usually if there's a load, it will throw it off, but maybe there's power op amps where they can provide significant current. You know, there's a bunch of variables. But for this video, we're just going to look at the LM358. We're using 1 out of 2. There's one over there. The one that you're not using, if this was going to be a permanent circuit, you probably want to wire as a voltage follower, where the plus is connected to ground, the minus is connected to the output, and you don't connect the output to anything. It's a short circuit to ground, basically. But that should lock it into place. Maybe prevent problems. I don't seem to have any problems with these op amps when I leave one just floating, you know, not connected to anything. But I have other integrated circuits where you see maybe effects on the circuit you got, but definitely you see wasted current from the power supply if you leave the inputs in those cases just floating. So it's good to tie them to something. Check the data sheet for the specifics of the integrated circuit you're using. So in any case, went on longer than I expected, but I hope you enjoy. Make sure you check out one of the other videos I posted on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.